Okay, so nobody showed up to the help session today, which is fine. I mean, usually I only have 5 or 6 or 7 people anyway, but I want to spend a little time, since I mentioned in class that it would be a good weekend to work on this free response question. Let's work through this. Now, you can find the solution to this online, but let's use this help session as a time to work through some of these free response questions, because your free response will be like this problem, where I'll give you 2 charges, and I'll ask you to sketch the electric field vectors. To do so, you imagine that there's a positive test charge there, and then you draw the forces that that positive test charge would feel. So I'm going to call this E2, modeled after, Q2 is up here. Oh, let's see, we'll call this one Q1 right here. And then this one will be called E1. So that's the first thing I do, is I sketch the electric field vectors. I will also need to know what is this angle right here. So recognize that I have a triangle, that if that vector is there, that I have a triangle that is 4, 3, and then of course this is going to be a 3, 4, 5 triangle, but I'll go ahead and do the square root of 3 squared plus 4 squared. That's equal to 5. And I want to know what is this angle right here. So to figure out that angle, I would say that theta is the inverse tan of 4 divided by 3. And then that's going to be equal to what? 53 degrees. So that's 53 degrees right there. All right, I'm going to go ahead and sketch in my coordinate system too. There's my y-axis, my x-axis. So next, for part B, I want to calculate the x and y components for the electric field vectors. Now, the first thing that I need to do is calculate what E1 is. That's kq over r squared, where q is q1. That's going to be 9 times 10 to the 9th. Q1 was 32 nanocoulombs, 32 times 10 to the minus 9 coulombs, divided by r, which is going to be 4 meters squared, and that's equal to 16. So this cancels with that and leaves a 2 in there. 32 divided by 16 is 2. Those 10 to the plus 9 and minus 9s cancel, and that leaves me with 18 newtons per coulomb. And then I need to do the same for E2. That's 9 times 25 divided by 5 squared. I left off the 10 to the plus 9 and 10 to the minus 9 because I know they'll cancel out. That cancels with that, and that's equal to 9 newtons per coulomb. So I have this one is equal to 9 newtons per coulomb, and this one is equal to 18 newtons per coulomb. Now, for part B, I need to calculate the x and y components. So if I redraw my coordinate system, I'm going to have, let's see, that is 9 cosine of 53. And 9 sine of 53. And then my other vector is 18 in the negative y direction. Okay, so now 9 cosine of 53 is equal to 5.4. So I'm going to redraw this, and you might do this. I recommend really that you do draw these pictures. It'll help you to sort of think through this. This is 5.4, and then the other is going to be 9 sine of 53 minus 18, and that's equal to minus 10.8. So 10.8 in the downward direction. So those are the x and y components right here of E1 and E2, and then these are the final components of that vector. So now I want to find the magnitude for part C of the electric field at part A. So C starts here. Define the magnitude of that vector. I want to know that vector right there. It's going to be the square root of 5.4 squared plus 10.8 squared. And that's equal to, let's see, that's 12. Let's see how many sig figs. Yeah, so it looks like I have 2 sig figs in the problem, so I'm going to keep it at 2 sig figs right there. So that would be the magnitude of that vector, 12 newtons per coulomb. And I don't ask for this, but let's ask what is that angle. Actually, I'm going to call it phi. That is the inverse tan of opposite over adjacent. The opposite is 10.8. Adjacent is 5.4. So it looks like the inverse tan at 2, which is 63 degrees. So 63 degrees below the negative x-axis. I don't ask this, but I could ask it of you on the exam. All right. Oh, no, I do ask it. Here, what is the direction? Show your work to find the direction of the electric field at point A. Notice that I do say show your work. So if you just write that angle, I'm not going to give you credit for it. So I want to see this work that you've done to get it. That'll help you, by the way, if you make a mistake in your calculator, you're in the wrong mode, or you just get them flipped or whatever, then you'll still get credit even if the number's wrong. Now at part E, if I place a 3 Coulomb charge at point A, what force does it experience? So this was D. E. F is equal to Q times the electric field. 3 coulombs times 12 newtons per coulomb. That's 36 newtons. So that's how I find that force. And then F, what is the potential at point A? Let's go ahead and do this. So I'm going to redraw this. I have 25, minus 25 and 32, minus 25 plus 32. And they're 3 and 4 meters away. So this is my point A. This distance is 4 meters. That's right. Yeah, and then this distance is 3 meters. To find the potential at this point, now this is new, we haven't done this, but we're going to do it in class. So let's go ahead and get this. First of all, potential is equal to an energy per charge. Potential is energy per charge, or we're going to see this in a variety of ways. It is a change in potential energy per charge, or we're going to write it as a work per charge. Voltage or potential is the same. Now be careful, because notice I use some similar words here, that when I'm talking about this is potential. And I know that we've used similar language to talk about energy. In fact, I did that here. This is potential energy. They are not the same. They're related, but they're not the same. Potential is an energy per charge. And I'm going to write it as potential energy so as to not confuse that with our electric fields. I'm not going to use E. Although we will find that kinetic energy can be related to potential. And we'll see that in a later problem as we move through chapter 2. Or I can describe it as the work. But if you remember from last semester, what was that, chapter 5, that energy, potential energy, work, that all those things are really related by the work energy theorem, that if I do work on an object, I change its energy. So the potential is an energy per unit charge. And then further, this potential is equal to KQ over R. We derived that expression, or at least we showed a dimensional derivation in class, or we will next week. Nice thing about this, scalar quantity. This is a scalar quantity, which should excite you. Scalar quantities excite me because I don't have to do vector addition with that. I can just add up the numbers. Remember when we did work and energy, and y'all were all very excited that this was a scalar quantity? That should excite you too here. So I hope that's good news going into the weekend, that you have material next week that is going to be mostly centered around scalar quantities. So if I want to know the potential at point A, what did I call this? Q1. This is Q1. This is Q2. My first step is just to calculate the potential due to each charge. So I'm going to calculate V1, and it's going to be KQ1 over R. That's going to be 9 times 10 to the 9th. 32 times 10 to the minus 9 divided by R, which is 4. So these cancel there. 4 goes into 32 at 8 times. So 9 times 8 is 72 volts. And then V2 is KQ2 over R. Watch this closely. 9 times 10 to the 9th. Q2 is minus 25 times 10 to the minus 9 divided by the distance, which is 5. Notice that this is r, not r squared, so I'm not squaring that denominator. And then also notice that I'm keeping this negative sign here. Now, it is a scalar quantity, okay? So the negative has nothing to do with direction. There is no direction associated with potential, but it does have to do with a change in potential energy. And we saw this in Chapter 5 of last semester, that I can have a negative change in potential energy that has nothing to do with, you know, the direction of that energy, because energy doesn't have a direction, but it has more to do with, am I giving or taking away energy? And that's similar here. So let's see, this cancels and makes 5 up there, that cancels there. So I get 9 times 5, or 45 volts, and then I carry that negative. Then if I want to know the total voltage, I'm going to have 72 volts minus 45 volts, which is what, that's 27 volts is the final answer. So be careful with that. Make sure that you're getting the negative sign, keeping the negative sign, and then also recognize that these equations are all really similar. That I have KQQ over R squared, that's my force, KQ over R squared, that's my electric field, and then KQ over R, that is my potential. So those equations all look similar. That's force, electric field, and potential. They look similar because they're all based on Coulomb's law, by the way. As we saw in class, that they're derived all from Coulomb's law, and so they look very similar. Okay, let's look at let's go and look at number 2. So this is based on the idea that our voltage, or our potential, is equal to a change in energy. So our voltage is equal to a change in energy over our charge. And notice here I didn't put potential energy because I'm talking about a change in energy that is a change in kinetic energy. So be careful, even though this is E, and we've been using E for electric field, that this is an energy. In fact, let's just put in a K right here for a change in kinetic energy. And I can calculate my change in kinetic energy. My delta KE is equal to my change in potential times our charge. And so that's going to be a change in potential. It's moving from an initial of 8 to a final of 2. So negative 2 minus 8 times Q. This is a proton, so it's going to be 1.6 times 10 to the minus 19. I'm not really concerned with is this negative or not, because I know that there is no negative kinetic energy. So I'm just going to get rid of that negative sign there where it's negative 10. I'm going to have 1.6 times 10 to the minus 18 joules. So that is the change in kinetic energy. And then if I want to know the speed of that proton, I would say, well, my kinetic energy is equal to 1/2 mv squared. And so that's going to be 1.6 times 10 to the minus 18 is equal to 1/2. The mass of a proton is 1.67 times 10 to the, minus 27 times v squared. I just point out here, so this quantity, the fundamental unit of charge, which is the charge of a proton, that's on your equation sheet. This quantity, which is the mass of a proton, that's on your equation sheet. And these equations are all, of course, on the equation sheet, except for this one. There are a few equations that you need to remember from last semester. Newton's second law, F equals ma. Our two kinematics equations, V equals V naught plus AT, and then X equals V naught T plus 1/2 AT squared. So as you've seen already, always when we're encountering these, those initial speeds are 0. So we can just leave those out. So V equals AT and X equals 1/2 AT squared. And then finally, our kinetic energy is equal to 1/2 mv squared. I'm going to put KE there for kinetic energy. Okay, you would solve this. I'm not going to deal with that, but you can solve that for V. Just solve that equation for V. Do the square root of those numbers to find B. Okay, and now finally, let's do this, and then we'll wrap up this and make it a really short help session. Oh gosh, this is really short. So we sketch 5 to 6 electric field lines for this configuration and use solid lines for the E field, and then sketch 4 to 5 potential lines. We did this in class, or in lab rather. We did it in class too. First of all, recognize that these are different charges. One's bigger than the other. One's twice as big as the other, so it's going to have twice as many lines. And this one's positive, so it's going to have field lines going from there to there. I'll just draw a couple lines there, and then realize that I have to have twice as many field lines, so that means I draw 2 more. So notice there are 2 field lines here, 2 field lines here and here, and then there are twice as many over here. There are 4. And these field lines then, they go off into infinity, or they're really, I guess, originating from infinity. And then if I want to draw my equal potential lines, remember, equal potential lines are perpendicular to the field lines. So they're going to look like this. I'm going to draw it as a dashed line. Notice that this angle is perpendicular. It's going to keep going around like that. Perpendicular, always perpendicular to the field lines, like that. All right, so those are my equal potential lines. Equal potential lines are important because the energy of a charge moving along that equal potential line does not change. Delta E is equal to 0 because, delta V is equal to 0. I'm going to put delta PE rather. And since those two are equal, or rather they're related because potential is energy per charge, that's why. If the potential doesn't change, the potential energy doesn't change. And then also I can say that to move a charge from here to here requires a work equal to 0. If you remember last semester we talked about this example of if you move a block in this direction, you're not doing any work on that object because you're not changing its potential energy. Okay? So that's true too, that those same ideas come back to this. I think we'll stop there. So take this weekend. This is a short help session, so if you're watching this and you're using this for extra credit, or just trying to get a little bit ahead, this is a good way to get ahead. Let's go ahead and master these problems. The first one is definitely going to be on your exam, and these other two, we'll see. We'll talk about it next week. I'm not sure. I might change one of them, but if they're not on the free response part of the exam, they're definitely going to be on the multiple choice part. So you'll need to know those things. So take this weekend and spend another 30 minutes or hour and practice this. Maybe print out this and do it all on your own without any help at all. Okay? Y'all have a good weekend. I will see you on Monday.